Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at curve sketching. Now, we've done curve sketching before, but we just looked at finding intercepts and the like. Now that we know calculus, we can get a lot more information about the graph, and this will come from the first and second derivatives. So let's look at some function that I've drawn here. So A, B, and C are known as stationary points. So that's because if I were to draw the tangent to the curve at each of these points, it would be horizontal. Now we know that horizontal lines always have gradient 0. So these stationary points occur whenever the first derivative is equal to 0. Now there are three types of stationary points. A is a maximum, B is a minimum, C is an inflection point. So you can see here A is a maximum. It doesn't mean that it is the largest value of the function overall. See, over here there are values that are much larger than the y value at A. It's called a local minimum because it has the highest value of the function in this neighborhood. Now when we say value of the function, we're talking about the y value. That is the value of the function. Now similarly, you can see that B has the lowest y value in this neighborhood. It's not the lowest overall because this graph would keep going. It's the lowest in this neighborhood. C is an inflection point, and I'll talk more about that in a second. But just note that at any stationary points, derivative is equal to 0, so we can find them before we graph some function. All we need to do is find where the first derivative is equal to 0. Now the first derivative also tells us about the gradient and whether it's increasing or decreasing. So remember, by increasing function, we mean as you go right, you go up. It means that as x is increasing, as we go right, y is also increasing. A higher value of x gives a higher value of y. Now, all of these yellow regions here are regions where the function is increasing. That means the gradient of the tangent would be positive, and so the first derivative is positive whenever the function is increasing. Of course, on the other hand, it's decreasing in this blue region here. So decreasing means as you go to the right, as x increases, you go down because y is decreasing. So in this region, if you had a higher value of x, you'd actually get a lower value of y. So a function is decreasing whenever its first derivative is less than 0. Negative gradient means it leans to the left, whereas positive gradient means the curve is leaning to the right. So that's the information we can get from the first derivative. What about the second derivative? It actually tells us about concavity. So there really are two options for a curve. It can be concave up, which is what I call a smiley face. That occurs whenever the second derivative is positive. The other option, it can be concave down, and that occurs when the second derivative is negative. What if the second derivative is neither positive nor negative? So if the second derivative is 0, it means you have an inflection point. So inflection points like this one here that we saw up here, they can either be stationary or non-stationary. At an inflection point, it's actually said the curve is both concave up and concave down. At an inflection point, there is a change in concavity. So here, the curve went from being a frowny face, concave down, to concave up. But this is not a stationary point because the tangent to the curve would look like this. It's definitely not horizontal. Here, the first derivative is still negative. The first derivative's not 0. So first derivative's not 0 means it's not stationary, but it's still an inflection point. There's another non-stationary inflection point here where the curve goes from being concave up to concave down. And at this stationary inflection point, it's gone from being concave down to concave up again. It's gone from being frowny face to a smiley face. So all of this will help us in sketching a graph. We're going to find this information from an equation first. So let's look at an example. So we're going to graph fx equals x cubed minus 12x. 6x. So the first thing I'm going to do is find the y-intercept. So that occurs when x equals 0, and I just get 0. So the y-intercept here is 0. So let's find the x-intercepts. So if 0 equals x cubed minus 12x, we can solve this easily through factorization. We get x outside of x squared minus 12. And so if that's equal to 0, we either have x equals 0, we already knew that it passed through 0, 0, or we get x squared equals 12. So x would be plus or minus root 12, which is 2 root 3, about 3.46. So the x and y-intercept, there's one there, and 3.46 is about there, and negative 3.46 about there. So the curve is going to go through those 2 points. So that part's not new, finding the intercepts. What is new is finding the first and second derivative. So the first derivative, you know how to do this. We just move the power to the front, decrease the power by 1. It's 3x squared minus 12. And then the second derivative is just move the power to the front, decrease power by 1. It is 6x. So how do we actually get the information we need from these? Well, it's really all about when they're equal to 0. So let's find where the first derivative equals 0. So if the first derivative is equal to 0, that means 3x squared minus 12 is equal to 0. So you get 3 x minus 2, x plus 2. So I just factorized it twice there, which I'm sure you know how to do. So we get x here equals plus or minus 2. What did I just find? Well, since the first derivative is 0 when x is plus or minus 2, that's precisely where the stationary points are. But I don't really know, are those stationary points maxima, minima, or perhaps an inflection point? We just don't know. So for that, we can use the second derivative test. What I do with the second derivative test is I substitute each of these values into the second derivative. So the second derivative was just 6x. So the second derivative evaluated at 2 is 12. And the second derivative evaluated at negative 2 is 6 times negative 2. So it turns out that if the second derivative is positive at a stationary point, that actually means you have a minimum. And the opposite is true. If the second derivative is negative at a stationary point, it means you have a maximum. Now just note again that these are local minima or local maxima. They may not necessarily be global minima or maxima. So make sure you're careful with this. It sort of goes the opposite way that you'd expect. Minimum occurs when second derivative is positive, maximum when second derivative is negative. Okay, so we know the x values of 2 and minus 2. What are the y values? Well, we just substitute in here. So f of 2 gives you negative 16, and f of negative 2 gives you positive 16. So I'm going to make this negative 16 and positive 16. So here at x equals negative 2 and 2, we've just found that this one here is a local maximum, and we've found here that this point here is a local minimum. Now the last thing I'm going to do is find possible inflection points. So that is where the second derivative is equal to 0. So the second derivative was 6x. So if 6x equals 0, x equals 0. That's a possible inflection point. Now, we call them possible inflection points because there are some pathological cases. For example, in the graph of y equals x to the power of 4, sometimes the second derivative equals 0 and it's not an inflection point. But for our purposes, this one is an inflection point. X equals 0, which is this point here, is an inflection. Now, notice that the only stationary points were at x equals 2 and minus 2. X equals 0, at that point, it's not stationary, because if you substitute x for 0, the first derivative does not equal 0. This is a non-stationary inflection point. So we can easily see the behavior by looking at the second derivative. Of course, for 6x, it is going to be positive. 6x is going to be positive if x is positive, and the opposite. 6x is going to be negative whenever x is negative. So what that means is the second derivative is negative, so the curve is concave down. It's a frowny face over here when x is less than 0. It's a smiley face when x is greater than 0. This is where the change of concavity happens. So we really now have enough to graph this. So we know the second derivative is negative over here, so it's concave down. It's a frowny face. So it's going to go like this. Now, it's going to change concavity at this point. So it's going to go from being concave down, it's going to now be a smiley face and concave up. And there we have the equation of the graph. You should make sure that you write the equation on the graph. So this is x cubed minus 12x. We are done. First and second derivatives really helped us here. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.